Hi everybody, hi, Mike here. Today we're going to continue with our learning, and you guys did a great, that's a lot of, jeez, my kid is like eating tortilla chips, and then the cat, I unplugged his fountain and now he's wondering what's, hold on. Okay, I'm back. That dull humming is his fountain, and he seems to be doing better. First of all, you guys did good on your third exam. I know it's different. I know it's a different system. So let's keep plugging along. We're going to go right to 6.4. We're going to skip 6.3 for now. And if you want to take a look at it, great. But it's a little bit beyond the scope of what we need to talk about, which is the organization of electrons in atoms. If we know the locations and properties of all the electrons in an atom, we can do a lot of predicting about how an atom behaves itself. So we're going to think about some of these concepts. Now, we've already talked about shells, right? Quantum levels. And we can think of this as kind of like having a ticket on a train. You could be on a certain train, in a certain car, in a certain row, in a certain seat. So as we talk about these concepts, we're going to become more specific. So shells are actually broken into subshells. All right. Subshells house orbitals, different numbers of orbitals, and those hold the electrons, which can have what we can think of as spin, which determines magnetism. So let's talk about shells first, and we already know about those because you already talked about quantum levels, but I'll talk about what that means in regards to how we're going to proceed. So you guys already know about shells, that's what we call them colloquially, but if you want to be fancy about these things, there's quantum numbers. Then there's a sort of slang. And so actually we're not going to have any slang for the shells. They're called principal quantum number, and you know they're n levels. One thing I don't think I really got to mention to you yet though is this corresponds to what row in the periodic table an element's in. So for example, you'll notice that the first row in the periodic table only contains 2 elements, and that's because the first shell can only hold 2 electrons. And then if you go out to the next shell, it holds 8 electrons. So as you go and find out that more electrons are in an atom, they become more complicated. What the hell was that? Something in the sink just shifted and it scared me. Okay, so let's talk about subshells. Okay, now I really want to emphasize, I'm going to try to uncomplicate this as much as possible. So we're really not going to focus too much on quantum numbers until later on, all right? Let's go straight down to talk about subshells. You're going to find out that within a shell, they can be broken into subshells, and the more electrons there are in an atom, the more subshells a quantum number would have. So basically, these shells can hold more electrons as you go down more in the periodic table. And so, but then you notice there's kind of areas in the periodic table where they're broken into kind of blocks. So for example, the first 2 columns of elements, you know, with sodium and lithium and potassium and the alkali metals and the alkaline earth metals, that's a block that's 2 elements wide because it has S-type subshells. And so that's going to be 2 electrons is what an S can hold. We'll get to that in just a little bit. And then there's P and D and F. And this is sort of a looser sort of way to talk about it than a bunch of different integers. All right? Let's talk about orbitals next. So within a subshell, you can have orbitals. That's the base resonance of where the electron is. And orbitals contain 2 electrons max, or they can contain 0, or they can contain 1. We'll get to that. And then as an electron is inside of a orbital, it can have a certain spin. So this is called spin quantum number. And it's, you know, ms plus or minus 1/2. You know, and then once again, we're not going to focus much on this. We have sort of shorthand notation for this stuff. So what we're going to do is here we're going to talk about which orbital it is using these letters. And then what we're going to do is we're going to symbolize orbitals as a dash, or sometimes you see a box, and sometimes you see a circle. And what we'll have with spin, it'll be an up arrow or down arrow. Let me try to explain why we're talking about spin. By the way, we're not really sure it's spin. There's a lot about electrons we aren't really sure we know, but we know that electrons cause magnetic fields, and we know that particles, when they move, if they're charged, they create a magnetic field. So we call this spin, and we think of it like, you know, counterclockwise or clockwise spin. And so what we'll do is we'll call an orbital a dash, and then we'll call spin an up arrow or a down arrow, and that'll take care of all the stuff that really is also represented by quantum numbers that go into really, really complex formulas called differential equations, and that's beyond the scope of this class. So let's start once again with hydrogen and talk about its neighbor in the periodic table, helium, or its row mate. Okay, let's talk about hydrogen first. Now look, folks, I know that was a whole lot of information, so let's take a really quick garden break.
Hey buddy, when's Mike gonna put us in the ground? He says we can't go in the ground until it's greater than 45 degrees at night. I'm so sick of this place. I just want to get out and flower and fruit. I want to flower and fruit too. Let's bust out of here. Yeah, let's go.
Okay, here we are in row 1, or period 1 of the periodic table, and we've got hydrogen with 1 electron. And so what I'm going to do is I'm going to symbolize the orbital as a dash. Remember, it could be a box, it could be a circle, and what we'll do is we'll put an electron in there. And the reason I'm putting it on the left side is because that's really half filled. An orbital will contain a maximum of 2 electrons, all right? And so I could have written this arrow going up or down. It really doesn't matter. Usually you just kind of, the first one you write is an up arrow. And so what we've got here is we've got an orbital that is half filled, and actually we have a name for this orbital. This is called the 1s. All right? An S-type subshell has only 1 orbital in it. We're going to get to that in a little bit. We'll talk about P and D and F. And so that's a half-filled orbital. And that's really important to know if it's full or half-filled, because half-filled orbitals, by the way, can make covalent bonds, and filled orbitals don't. So now let's talk about what happens with helium. All right, so what we kind of think about is we got to know how many electrons is in an atom. We kind of pile them into this template of where the electrons go. So the first electron in helium, this is a 1s too, 1s also. You know, I'll put just like that. Now, there's rules about what has to happen with the second electron. It's really what nature has happened. Now, folks, you might ask like some of this, like why, and there's a lot of like no one knows. All right, so just accept this, that an electron, if it was going to go in, the second electron to that orbital, it has to have opposite spin. So it has to actually have the opposite spin of the other electron. So let's talk about what doesn't happen, okay, in nature. What doesn't happen is that this orbital fills up with 2 electrons of the same spin, no matter which way. All right. Now these things have fancy names, these rules. I'm going to tell you this thing. Its rules called the Pauli Exclusion Principle, which sounds fancier than it is. It's basically saying that an electron can't go next to another electron with the same spin in an orbital. So neither of these happen. And here's how the best way I can explain it, folks. This would be like we talked about spin causes magnetism. If you try to stick two north poles of the magnet next to each other, they're going to repel. But if you flip one of the magnets around and you put the south and the north pole together, they'll be attracted. And so you can't jam two electrons into a orbital unless they're opposite spin. All right? You can have a half-filled orbital and it can spin whatever way. Matter of fact, this thing could turn its spin around. It takes very little energy. You could actually zap hydrogen with microwaves that would make this reverse its spin. And that's kind of, we're getting to how MRI works, magnetic resonance imagery. You're just getting hit with very low level radiation. So there's a couple more things I got to talk about is the terminology here, which we're going to continue talking about later on. If an atom has one or more unpaired electron, we call this paramagnetic. Now I want to talk about this. That prefix is not spelled the same way as the word pair, P-A-I-A-R. So this does not mean that electrons are paired. Much to the contrary, it means one or more unpaired, one more electron with unpaired spin. So if you got in an orbital or orbitals, you've got electrons that are not having their spin canceled, that's called paramagnetic. So hydrogen would be paramagnetic. All right? Helium would be called diamagnetic. Don't worry, when we do more examples in the next video, we will always talk about paramagnetic and diamagnetic. This is all electrons are of paired spin. Now you might remember hydrogen is one of the noble gases. It has a filled n level. And you're going to find out whenever you fill an n level, or even a subshell, you're going to have an element that's diamagnetic. So this would be unaffected. This would be unaffected by a magnetic field. It doesn't have a net magnetic field. That spinning electron cancels that spinning electron. And this does have a magnetic field. If you had just a single hydrogen atom, it would be paramagnetic. Okay, let's talk about, this is a lot today, and you guys just got done with your exam, so let's talk about where we're going in the future. Okay, to be continued next time. We're going to talk about atoms that are more complicated because they have more electrons. So you know that oxygen's not in the first row, it's in the second row, which means its quantum level, n level 1 is full. And it turns out, now don't worry about why. We'll talk about why next time. The more quantum levels there are in an atom that are occupied by electrons, the more subshells there are. Each quantum level adds another subshell. So there's p-type subshells which have 3 orbitals. And what we're going to do, and so I wrote these 3 orbitals as 3 dashes. You could write them as 3 circles or 3 boxes. And now we're going to show how those 8 electrons go and pile in to those orbitals. Now there's room for 10 electrons, but there's certain other rules besides not being able to pair their spin within an orbital. There's other rules as to how they occupy those. So let's talk about that next time, and I'll let you digest this. It's a little bit different, but if you don't like math, we're not going to be doing much math, folks. The most you'll have to count up to is 120 or whatever, because we're just going to be counting electrons for quite a while. So none of the deep math is going to happen. We will see you folks next time. Stay safe. Bye.